Okay, so this video is designed to go through the derivation at the beginning of section 7.4, which has to do with arc length. So remember, when you're talking about arc length, you can imagine some kind of function. So there we've got our coordinate axes, and let's just imagine some kind of arc. This can really apply to any function that you can possibly imagine. But we're going to think about the length of that arc from some spot A up to some spot B, and this is supposed to work for any arbitrary function. So when you're thinking about the length of something, what might come to mind first is the distance formula. So if we plotted point A on this arc and point B on this arc, one way to approximate that the arc's length would be to just figure out how far, oh my gosh, and that looks like it's bent, but how far A and B are from each other. So let me try to redraw this. So there we go. So we'll say now B is kind of up here, A is kind of right here, and one way to approximate the arc length is to find the length of this line. So that would be using the distance formula, right? So of course that looks like it's an under approximation here. It looks like the length of the arc with that curve in it is a little bit longer. But that's pretty much the idea that we're going to do. We're going to take A, cut it up into a whole bunch of subintervals, in fact n subintervals, as we've done for a lot of the rest of this chapter. And then we'll basically just take lots of, after we cut this up into lots of subintervals, you know, lots of chopping here, we're going to add up lots of little pieces of lines, and there'll be an integral at some point, so let's kind of see where that integral comes from, and basically we're just going to do the distance formula lots of times. So here's the next part. So here's a new arc, right? So we've got a new arc. We're visualizing it from A to B, so it looks like A is right here and B is right here. And it's been cut up, or partitioned, as they say in mathematics, into n subintervals. And now we're just basically going to do the distance formula on each one of those subintervals, right? So if you've got like the ith subinterval, then you take the x sub I minus the one previous to it and square it, plus you do the same for the y values at those points, and that's the distance formula, right? So this is, I guess I can write it in there. So this is the distance formula applied to the ith subinterval. So I'll write that down, to the ith subinterval. Okay, so that's all that part is. And then why is this sum in front of them? That means it's adding them all up, right? Well, like I said before, you're going to want to add up all those little distance formulas that you have in order to get the total arc length from A to B, right? So that's why there's a sum in front of this guy. So then we just start using some fancy notation. So the distance between x sub I and its nearest partner node, x sub I minus 1, that's just the change in x sub I, right? And the same thing for here, that's just the change in y sub I. Okay, so we have that, and then let's see, what did they do on the next step here? It looks like they multiplied by a clever 1, right? So right here, you've got multiplication by a clever 1, and that clever 1 was delta, or the change in x sub I squared. So why did they do that? I think they did that so that they could factor it out. See, on the next step, they factored it out. So let's write one more step in here. So that's equal to the sum of the square root, and now we can factor this out. So we're going to factor out the delta x sub I. So if we factor that out, delta x sub I squared, right? So if we factor that out way out here, then what's left? 1 is left there, and what's left here is going to be plus, we factored out this part, right? So it's going to be plus and I'll do it in green, delta y sub I squared over that other delta x sub I squared that came from our clever one that we introduced. Okay, so so we factored it out, and now since this is a product, you can cancel the square root and the squared on this one, and that's how we get down here and the squared has disappeared. Anyway, that's pretty much the formula for arc length right there, except we've got a sum of lots of delta x sub I and delta y sub I subinterval pieces. So if you remember, if you take the limit as you shrink that subinterval size down to 0, right? That's what they're doing here. Take the limit as the subinterval size goes to 0 of that guy that we have right there. Remember, the limit of a sum is you guessed it, an integral. So our first node was at A, our last node was at B. Limit of the sum is that integral, and then we have the square root of what's left, 1 plus delta y sub I over delta x sub I. Isn't that just slope? And when we took the limit of the sum, that slope becomes instantaneous, so it becomes like dy, make it instantaneous here, dy dx squared, and then out here that becomes dx. And that's the formula for arc length. So there you have it. There's it with Newton's notation as f prime. So the arc length, which we're going to call s in most of our problems, of a curve, and we can pretty much do this with any curve, any piece of any curve. So if that's your curve, you can go from this A to B, or you could go over here and find that little piece of arc. All you've got to do is integrate from the bounds of the curve and integrate the square root of 1 plus the derivative of that curve squared. So a pretty neat formula. So if you're asking yourself, like I used to when I was in high school, where does the why the heck in the arc length formula do you have this square root thing? Remember, it all goes back to applying the distance formula to little subintervals and then taking the limit of a sum, and it comes out to be an integral. That's the whole theme of this chapter. Okay, hope you found this enlightening.